Do you hear me? Great. All right. Let's see this example. We have a seesaw and put its mass is 0. Wow. I started to write something on the table, but I can't see it. Just a minute. All right. We have a massless seesaw and place M1 and M2 at R1 and R2. So the origin of the coordinate system is there, and also this is the axis of the rotation. How can we calculate what is the condition for the balance? So we put something here and here. This is the origin of the coordinate system, plus this is the axis of the rotation. How can we calculate the torque of this force with this displacement vector? By definition, the torque equal R cross F. If you use your right hand, the A means the R and the B means the force. Can you answer what is the direction of R cross weight? I draw it again because I need more space. Mass 1, weight 1, R1. What is the direction of torque 1, which is R1 cross G1? What is the direction of torque 1? Just look at this plot and these directions. Is it in the plane of the table of your screen? If yes, why? If not, why? So, what is the direction of tau 1? And then think about what is the direction of tau 2, torque 2, which is R2 times G2 vectors. Anybody? I give you 5 minutes, I pick up a new pencil. Alright, I'm back. Have a new pen. Clockwise direction. In my coordinate system, this is the clockwise direction. Do you mean clockwise? We have torque like this and this. Use your right hand, so I can't. Wow, what if I switch on a camera? You won't see me. All right, I try to do it on the whiteboard. So if this is the R1 and this is the G1, place your finger parallel to the R1, this finger, and the other with the G1. In that case, this finger will points towards the U. So it came out, it's perpendicular to the plane. If I want to, so this is the tau 1, comes from the plane of the table to U, and the other goes behind the screen, behind the table. So these are the tau 1, tau 2. So if you have two vectors in the plane, the cross product of these two vectors will go out of the plane. So it can't be in the plane of the two vectors, it can't be in the plane of the screen. It goes out of the plane. Technically, it's always perpendicular, and its size depends on the angle between the two vectors. If it's 90 degree, sinus 90 is 1. Its nominal value tau 1 will be G1 times R1, and these are not vectors, these are the nominal value. So for example, if the mass 1 is 10 kilogram, this is 100 Newton. If the R1 is 1 meter, the tau is 100 Newton meter. And it comes out of the plane of the screen and points to you. So again, see, so mass 1, mass 2, this is the R1 G1, and the torque will come out of the plane. And let's choose a positive direction. If we want to sum all of the torque, the first one is a positive tau 1. It's a positive G1 times R1. What about the others? R1 is this one. R2 is this one. G2 is this one. This torque will go behind the screen. And since this is opposite with the positive direction, this will be minus tau 2. So minus G2R2. What is the condition of the balance? This has to be 0. What does it mean? This has to be 0, but don't forget it's only true if this is 19 degree. If we have a seesaw like this, mass 1, R1, the angle is not 90, we have to play with the sinus theta. So that means G1 R1 equal G2 R2, and you can imagine if you sit closer to the origin and somebody else sit on the other side of the seesaw but further from the origin, your mass has to be larger than the other's mass to balance the seesaw. What does it mean with numbers? Wait, I forget to send the link of this table. So if, for example, mass 1 is 10 kilogram, mass 2 is 15 kilogram, R1 is 2 meter, where should I place the M2? G1 is M1, G2 is M2G, so M1G times R1 has to be equal M2G times R2. We can forget the G. If we are looking for R2, R2 equal M1 R1 divided by M2. In this case, this is 10 times 2 divided by 15, which is 1.3 meter. So it has to be 1.3 meter. You can find here more interesting and more detailed example how to calculate the condition for ladder. It's worth to check. These are the so-called rigid objects. This can translate and rotate. The dynamical equation, so technical rotation form of Newton's second law, is the sum of the torque will be equal to the moments of inertia times angular acceleration. This is for rotation. And for translation, the net force equal m times a. Let's go back to the seesaw example. We solved the equation for sum of the torque has to be 0, because 0, the balance means the alpha is 0, so the sum of the torque has to be 0. What about the translation? We have a G1 here, which is 100 Newton, and the G2, which is 150 Newton, is here. What is the sum of the forces of this system? Can you answer it? In this example, what is the sum of the forces? So again, let's choose a positive direction. This is the positive, and this is G1 plus G2, which is 250. That has to be equal to m times a. If we keep this example as it is, only calculating the net torque, we should worry about what it means. It means, since this is non-zero, we have a total mass of 25 kilogram. This seesaw should fall towards to the center of the earth with the acceleration 10. So this is a free fall. Why? Can you tell me where is the force that can compensate the two mass on the seesaw? Because if we leave as it is, the sum of the forces is non-zero. That means since the net force is equal m times a, the Newton's second law, it should fall down. But if you go to a playground, you can't see it. Where is the missing force? we need some other forces because it's nonsense. This seesaw won't have any angular acceleration, but in this case it should fall down. Upward direction the center. Great. This is a reaction force. It's the same story. So if you place a box on your table, this box has a weight, but the table and between the box there will be a so-called reaction force that comes from the structure of the table that can compensate the weight. Also, we have to compensate these two weights, so this has to be 250 Newton. And now let's go back the sum of the torque. We know this is a plus torque 1 minus torque 2. This is the torque 1, torque 2. What is the torque from this reaction force? How can we calculate? How tries this force rotate this seesaw? Is it any Newton meter? And don't forget the definition. Torque is the level arm times force times sine of theta. What is the torque from this R force? All right. Draw again. Now, for fulfill the balance G1, G2, R, this can guarantee the sum of the forces, which is m times a, has to be 0 because we can observe there is no acceleration. And now just go back. What is the sum of the torque? There will be a plus G1 R1 minus G2 R2. And what should I write here? What is the torque? How this force tries to locate? All right, what I want to say, this is the axis of rotation. If the force, let's just move it here, if the force goes through the axis of the rotation, this level arm is 0, because the level arm, by definition, the distance between the line of action, which is technically the vector of the force, the distance between the line of action and the axis of the rotation. If it goes through the axis of the rotation, this d is 0. So this is r times 0 because it goes through the axis of the rotation. There is no level arm. We have level arm here R2, we have level arm here R1, but for the R reaction force, the level arm is 0. Is it clear now? Rigid object, we always have to solve this equation, sum of f equal m times a, and sum of the tau equals moment of inertia times alpha. These are the basic equation, the rest is only some parameter like static friction, and so on. Is it clear? Please answer in the Discord, because if not, we can go through it again. Anybody else can join to my smart cup? All right. Here we have a seesaw. Let's put the origin of the coordinate system here. This is the origin, and also this is the axis of the rotation. Put an M1 body here. Its weight is the force 1. Let's say this is G1. We have to find the position of the action point of the vector. This is R1. Let's place another box. It has also a weight. The action point of the vector of the force is at R2 position. This is a rigid body. Means translation plus rotation are possible. What is the dynamical equation for translation? This is the well-known Newton's second law for the net force. And what is for rotation? Sum of the tau equal moments of inertia times alpha. Now the balance means no acceleration and also no angular acceleration. How can we fulfill these conditions? Let's start with the number 1. What is the sum of the forces? Let's choose a positive direction for translation. The sum is G1 plus G2, but to fulfill the condition A is 0, we need a reaction force here. And since this is the only point the reaction force can start, the reaction force can't start here because there is nothing under this piece of wood or something. The reaction force starts here. Since it goes upwards, this is a minus sign. This has to be equal. Since A is 0, M times A is also 0. It has to be 0. That means if this is 10 kilogram, if this is 15 kilogram, as in the example, this 250 Newton minus R equal 0 means R equal 250 Newton. That's translation. Let's talk about rotation. What is the sum of the rotation? If we use this right-hand rule, the tau 1, it's hard to draw in a whiteboard, that came out of the plane towards the U. Again, let's choose that this is the positive direction, so we have tau 1 with positive sign, and if it goes backwards, this is minus tau 2. Since this is 90, the tau 1, the nominal value of the torque 1, is nothing else just R times G1. So if it's 2 meter, if it's 10 kilogram, means the weight is 100. This is 200 Newton meter. What is the torque of the mass 2? The R2 is unknown, but we can see this is 90%. The nominal value of torque 2 will be 150 Newton times R2. All right. Don't forget something. That here we have a third force. This R, what we needed to compensate the G1 and G2. What is the force? Whether it's plus or minus doesn't matter. What is the force? What is the torque? Comes from the reaction force. You see here we have R1 times F1. What is the distance between the origin and the wait a bit. What is the distance between the line of action of the force that goes through the origin? How far is the vector from the origin if it goes through the origin? What is your distance from your table if you are at the table? Waiting for answer in Discord. What is the level arm? Thanks. Thanks, Sarah. So it's R times 0. Things, this part we can forget. This force does not rotate the system. Therefore, since this is moment of inertia times alpha, and this alpha has to be 0 for balanced, this tau 1 equal tau 2 because of the plus and minus sign, and that can give you R2 equal M1 R1 divided by M2, and that will be this 1.3 meter. I shared it. Alright, now you can come. A massless seesaw again. Let's put a weight of 100 kilogram. This is the G1, R1. And 80 kilogram on the other side. And this is R2. What is the R2 if R1 equal 4 meter? What is the R2? Calculate it and also tell me what is the reaction force. what is the magnitude of the reaction force. And solve it now, please. Waiting for the answers in Discord. Thanks, that's correct. And what about the R, the reaction force? Thanks. Uh, I think it's a very easy example that can be part of the test 2 or the exam also. Let's go further with a bit more complex example. And this is the pure rolling. Uh, what does it mean, pure rolling? You can imagine pure rotation. This is a fixed axis body that rotates with the omega. And this is a pure translation. So without any rotation, you just move this ball. And what if the V equal R times omega? If the V equal R times omega, if this is a pure rolling, the V of this point will be omega times V, and this is omega times R, and this is omega times R. If you use the same omega times R velocity, here you have also V that's omega times R and omega times R. What does it mean? If you mix these two motion in the middle, since this is in the middle, it's a fixed axis rotation. It's 0. In the middle will move. The middle will move with V. Upper part V and V again is 2 times V. And the lower part, since these are the same, that will be fixed. So you can understand the pure rotation by supposing that this point, when it touches the road, so for example, when the wheel touches the road, it's fixed. And when it's fixed, you need some force that can fix something, and this is the static friction. So pure rotation technically equal to the condition of the static friction. Let's start to solve this example. So here we have a surface and a cylinder, a barrel. It has a center of origin, and we pull this barrel with the force F. It has a mass like m, a radius r, and the force that can rotate the wheel, in this case this is the T, this is the static friction. If you remember for the incline example, at the very beginning we don't know whether the box moves. We have to check whether the static friction is smaller or equal to the mu times perpendicular forces, and the only perpendicular force here is the weight of this wheel, of this cylinder. This is a rigid body, so we have two equations. One is for translation. The sum of the forces will give you m times a, and for a rotation, the tau equal moments of inertia times alpha. Pure rolling. Let's assume this is a pure rolling. For the pure rolling, where it is, we know that the V is not independent from omega. The pure rolling means the velocity depends on the angular velocity, and technically the velocity for pure rolling will be equal to the angular velocity of this cylinder times r, and the acceleration is angular acceleration times r. So this is equivalent with the pure rolling. Alright, here we have all the equations we need to solve the example. Let's see some numbers. R is 1, m is 100 kilogram, force is 450 Newton, and mu equals 0.6. Let's start to write the conditions. One is the translation, second is the rotation, and the third one is the puration. So we suppose it's a puration, it's a pure rotation. That's just an assumption. It's a pure rotation. Means, what is the sum of the F? The sum of the F, the force we pull the body, and let's say this is the positive direction, minus T equal m times a. What is the sum of the rotation? Again, if a force goes through the x of the rotation, there is no rotation from this force. There is rotation only from the friction. Friction, what is the lever arm? The lever arm is the R. That will rotate the body via the moments of inertia, which is 1 over 2 m r square, and this is the alpha here. But we also know the condition for putation, what we assumed, a equals alpha times r. Here we have 3 unknown and 3 equations. Try to solve it now. Just use these numbers. Technically the solution is also here, but at first try to use these numbers and try to solve it alone. And answer what will be the acceleration, but not only copying from the presentation, but try to understand. Alright, let's check what you did. You only write 450 for the F equal 100 times A. TR, this is T times 1. 1 over 2m is 50. And C, if we write here, instead of alpha, A over R, that will be 1 times A. That will be A. We can write, no, not that. We can write the T here. That means 450 Newton minus 50 A equal 100 A. 450 equal 150 A, and A will be 3. Now just go back with this A here and say the T has to be 150 Newton. we should check whether the static friction can be large enough. This is 150, has to be equal to 0. Yes, this is the 0.6 times weight. The weight is 1000 Newton, so this is 600 Newton, which is true. So that means with that mu, with that force, with this M and R and the shape of cylinder, that can fulfill the pure rotation, and it will move like A equal 3m over s square, and from this one the alpha will be A over R. Since this is 1 meter, alpha is 1 over s square. You have to be able to write these equations from the dynamical equations of the motion of the rigid body plus from the condition of pure rolling, by assuming this is the pure rolling. If you can solve it, you should double check whether it's really pure rolling, and if yes, these are the results. A equals 3, alpha 3, T equals 150 Newton, and in that case you solve it. Next time we will see how to solve it if the mu is small, and unfortunately it won't be true. So pure rotation means the mu is large enough to have enough static force to rotate the body, like the condition of the pure rolling, which is a pure rotation plus pure translation you can find in the presentation. I will have soon another seminar, so need to be prepared myself. Do you have any questions? Then thanks, and thanks for your participation, and see you next week.